Okay, for this last piece that we have regarding numerical methods, I just want to mention that there is a certain Achilles heel with the numerical methods approach to solving differential equations. Okay, now one upon which we are going to have the numerical methods to work. Say we have the derivative of y with respect to x. Okay, a first order is equal to x squared plus 4x plus 3. And we'll say we have an initial condition, y naught is equal to 1, and we want to find out, okay, just what y of 3 is equal to. And now, say if I'm looking at solving the differential equation interactively. Okay, so I got on the screen d over dx of y of x is equal to x squared plus 4x plus 3. And if I throw in the condition, so I have y at 0 is equal to 1. And I'm looking at solving symbolically. Okay, so I have y of x is equal to 1/3 of x cubed plus 2x squared plus 3x plus 1. Now I'll get out of this screen. And let's say that I'm looking at evaluating at x is equal to 3. So I can evaluate at a point. And so we have with x equal to 3, and it's going to turn out that for the exact result, we had that y of 3 is 37. And now taking what we have with the numerical methods. Okay, so we have with the numerical methods, okay, so we have with the Euler approach, the improved Euler, and the official Runge-Kutta. Okay, we have with the Euler method, okay, so you have the opening statement is Euler, and we have, again, the differential equation. We have y naught is equal to 1, and we want to find out just what y is going to be whenever x is equal to 3. And so I took the step size, okay, to be at 0.2, so we have the number of steps is going to be at 10. And so we have with the Euler approach, we have 33.895, okay, not exactly 37. And we have with the improved Euler, and again, the opening statement is Runge-Kutta, and the submethod is the Hoyne submethod. And with the improved Euler, okay, so the output we have at 37.045, and then we have with Runge-Kutta, okay, again, you have the same opening statement, Runge-Kutta, submethod is RK4, and this comes out exactly to 37. Okay, so again, we have the pattern Euler, only so accurate, and again, if I had expanded the number of steps, let's say to 20, okay, I'd be getting closer. So if I took out to 50 steps, okay, getting closer. And for the Euler to work, so if I took this out to 100 steps, I'm still not as accurate as I am with only 10 steps with the Runge-Kutta. Now, again, so we do have the pattern. Euler is only so accurate. The improved Euler, substantially more accurate, and then we have with the Runge-Kutta, okay, highly accurate. Okay, but there is a limitation with the numerical methods. Okay, now there are some limitations with numerical methods, and we'll take, say if we're looking for the approximate or the exact answer, okay, we'll say we have dy over dx is equal to the square of the sum of x and y raised to the second. Okay, and if I'm looking at solving interactively, and we'll say that for the initial condition, we'll say that y of 3 is equal to 1, and solving symbolically. Okay, so this is what we have here. Now, if I'm looking at evaluating, let's say at x equal to 5, and say if I approximate, okay, so I have about minus 4.1813662, and now an equation like this will not be so easy to carry over. And so for what we have over in trying to work this out in the use of the Euler, improved Euler, and the Runge-Kutta, we'll look at this in just a moment. Okay, so we have with the Euler approach, okay, so I got Euler, and got this equation. Again, I had that y of 3 is equal to 1, and we're trying to find out just what it's going to be whenever x is equal to 5. And okay, and we'll say that for this one, for the Euler, we'll just break this up into, let's say, 10 steps. And we'll just carry this out to 10 digits. And notice we have a very large number in this case, so we're going to be way off the mark, it looks like. And if I take what I have and try to apply the improved Euler, okay, so we have with improved Euler, again, the opening statement, have Runge-Kutta, so you got the same equation, x plus y of x squared, y of 3 is equal to 1, x equals 5. We got the submethod, equals Hoyne, digits is equal to 10. Okay, if you notice, we got infinity, and then trying out what we have with the Runge-Kutta. So method is RK4. Okay, and so we have float going out to infinity. Now we have with the Euler, we have a number that is astronomical and is beyond what many a scientific calculator can hold. And we have with the improved Euler, you have going out to infinity. And with the Runge-Kutta, we have going out to infinity. And so you got the same equation, same initial conditions, but so these are way off the mark in comparison to what we have with the exact answer or the approximation thereof. So you have to be right at minus 4.8. And so basically anything that has like a mix of trig and inverse trig functions in the solution, in the general solution, is likely going to be, or has a high chance of being problematic for the numerical methods, and this equation is one such case.